America spent $13 billion building a warship the world had never seen. An enormous floating fortress promising more power, more sorties, and fewer crew members than any carrier before it. But just months after its debut, a single flaw threatened to sink not just the ship's reputation, but the entire future of United States naval dominance. What could possibly go wrong inside the world's most advanced supercarrier? And what did it take to restore her? Stretching more than 1,100 feet from bow to stern, the USS Gerald R Ford dominates the horizon like a floating city. Its flight deck alone covers 4.5 acres, longer than 3 football fields placed end to end. Fully loaded, the ship displaces nearly 100,000 tons, weighing more than the entire Brooklyn Bridge. Every detail of its construction signals ambition on a scale rarely seen outside of space exploration. Commissioned in July 2017, the Ford became the most expensive warship ever built. The final bill reached nearly $13 billion, a figure that dwarfs the cost of some entire navies. That price tag covers not just steel and electronics, but also years of research, new manufacturing methods, and the labor of thousands. From the twin nuclear reactors buried deep below deck, to the intricate maze of cables and conduits that power its systems, the ship represents 2 decades of American engineering and industry. The Ford's size and cost are more than numbers. They are a statement. This carrier is designed to project power anywhere on the globe, carrying dozens of aircraft, hundreds of missiles, and a crew that could fill a small town. Its presence alone can shift the balance of a region. With so much invested both in dollars and national prestige, any flaw or failure carries consequences far beyond the ship itself. Power is the backbone of any modern warship, but the Ford class takes this to a new level. Deep inside the hull, twin A-1B nuclear reactors churn out nearly 3 times more electrical power than the older Nimitz-class carriers. This surplus is not just for lights and radar. It unlocks a new generation of systems that demand far more energy than their predecessors ever could. At the heart of flight operations is the electromagnetic aircraft launch system, known as EMALS. Instead of relying on steam catapults, EMALS uses electromagnetic pulses to hurl aircraft from the deck with precise control. This allows the Ford to launch everything from heavy fighter jets to lightweight drones, one after another, with less wear and tear on both planes and crew. Paired with the advanced arresting gear, which uses electromagnetics instead of hydraulics to catch incoming aircraft, the ship can recover and launch planes faster and more safely than ever before. The numbers tell the story. On a high-tempo day, the Ford can generate up to 270 sorties, about a third more than any carrier before it. Automation runs through every system, from ordnance elevators to the galley, trimming roughly 600 sailors from the crew compared to the Nimitz class. That means fewer people exposed to danger, lower operating costs, and more space for advanced technology. These innovations were meant to keep the Ford ahead of any threat, but every leap forward brings its own challenges. Not all of them would stay hidden for long. January 2018. The Ford was underway off the Virginia coast, its engineering teams running through a checklist of sea trial drills. Deep in the propulsion spaces, watchstanders monitored dials and readouts as the ship's 4 massive propeller shafts churned through the Atlantic. Then, a warning light blinked on. The number 2 main thrust bearing, one of 4 critical components transferring the force of the nuclear reactors to the water, showed a sudden temperature spike. Gauges read nearly 100 degrees above normal. Instantly, the propulsion watch team sprang into action, following emergency shutdown procedures designed for just this kind of crisis. Power to the affected shaft dropped. The Ford's speed fell as the ship limped into a holding pattern, every eye on the engineering deck fixed on the bearings readout. The captain ordered a reduction in speed, and the decision came down to return to port. The message rippled through the ship. A brand new supercarrier, hailed as the future of naval power, was now facing a problem that could cripple its heart. For the engineering teams, the moment was both routine and extraordinary. Every carrier faces mechanical hiccups during early trials, but a main thrust-bearing failure is rare, especially on a vessel built to push the limits of technology. As the Ford turned back toward Norfolk, the crew began the painstaking process of logging every detail: vibration patterns, temperature readings, and the sequence of alarms. The watchstanders, trained for years to handle emergencies, worked through their checklists with calm precision. Above them, the rest of the ship's company waited for answers, the hum of machinery now edged with uncertainty. The world's most expensive warship was headed home, not in triumph, but in search of the flaw that had brought it to a halt. Inside Newport News's colossal Dry Dock 11, the USS Gerald R. Ford settled in for a repair effort that would test both the shipyard's workforce and the patience of Navy leadership. The investigation into the propulsion failure quickly zeroed in on the main thrust bearings, critical gears that transfer the immense force from the ship's nuclear reactors to its propeller shafts. Inspectors traced the problem to a precise cause: machining errors at the General Electric facility in Lynn, Massachusetts. Bearings had been cut out of tolerance, a flaw invisible until the stress of sea trials brought it to the surface. With the root cause identified, the challenge shifted from diagnosis to action. Over the next 15 months, more than 800,000 hours of labor would be poured into the carrier. Teams worked around the clock, stripping down the propulsion spaces, removing the defective bearings, and remachining or replacing components as needed. The sheer size of the parts, some weighing several tons, meant that even routine tasks required cranes, custom jigs, and careful choreography. Every move was documented, logged, and double-checked. Responsibility for the error fell squarely on the supplier, but the burden of repair landed on the shoulders of welders, machinists, and engineers at Newport News. Their work unfolded under the pressure of missed deadlines and mounting costs. Each day in dry dock was a reminder that the world's most advanced warship had been sidelined by a flaw measured in fractions of an inch. Yet through methodical effort and relentless focus, the team brought the Ford back from the brink, preparing it for a new round of testing that would determine whether the repairs had truly restored the promise of America's flagship. Once repairs wrapped up, the Gerald R. Ford faced a new round of scrutiny, this time from her own engineers, pilots, and technical crews. The first step was the fast cruise, a simulated at-sea period conducted entirely in port. For days, the ship's systems ran non-stop as if underway, with every department drilling emergency procedures, shifting power loads, and running diagnostics on the freshly overhauled propulsion plant. Engineers monitored the main thrust bearings hour by hour, logging temperatures and vibrations to catch any sign of recurrence. With those numbers holding steady, the ship advanced to propulsion trials. Nuclear technicians brought the twin reactors to full output, sending thousands of horsepower through the repaired shafts. On the flight deck, test pilots prepared for the first launches using the electromagnetic aircraft launch system since the overhaul, coordinating with deck crews and control room operators to prove the system's reliability. Each test checked off another requirement for radar, communications, and nuclear safety, until every system met the Navy's strictest standards for operational clearance. Fleet planners faced a hard reality. Global carrier coverage was stretched thin, and every day the Ford remained in dry dock left a gap in the Navy's forward presence. When the ship returned to active service, it wasn't just another vessel rejoining the ranks. Its re-entry restored the ability to project air power across oceans, to deter rivals, and to reassure allies from the Mediterranean to the Pacific. For Navy leadership, the Ford's comeback signaled a surge in readiness at a moment when carrier availability was under pressure worldwide. With its advanced systems online, the ship could now generate more sorties, support more missions, and anchor a strike group that would otherwise be forced to wait or operate short-handed. The return of the Ford to the fleet was more than a technical milestone. It was a strategic turning point, restoring a vital piece of the nation's maritime strength at a time of real demand. Right now, the USS Gerald R. Ford sails as proof that technological ambition carries real risks and real rewards. As rival navies accelerate their own advances, every fix and failure aboard this ship shapes the future of global power. The next test is already on the horizon.